the background for this talk, and actually the title of this talk, is that, well, philosophy of measurement now has seen sort of an upswing in interest, and the people who have been working on this, or many of the people who have been working on this, have been often very adamant about the need for a completely new way of conceptualizing measurement and well, thinking about how it connects to the sciences and to our general philosophy of science. And so basically, when I read that, I thought, oh, gee, now I have to learn all this new stuff. And so, and while I'm very happy with the learning about the new results, about the subtleties of measurement, it's a bit disconcerting for me, because I have a bit of a logician's mindset, even if not the skills, that to have to throw out all the nice conceptualizations that we already have just to incorporate some new stuff. And so my goal then is to see how far we can get with our old frameworks. And so this is what I'm going to be doing. And so the core point, or the core suggestion that I want to make, is that we can do fine with our old frameworks if we just distinguish cleanly between measurement on the one hand and standardization on the other hand. And here's an example. We want to measure the distance between the Earth and the Moon. And one very straightforward way is, and the classical way, is to just put two telescopes somewhere at different points on Earth, look at the Moon, and then do a little bit of trigonometry, and then calculate the distance of the Moon with the help of the angles that the telescopes have relative to each other. If you are really ambitious, you can go to the Moon in a rocket and measure the acceleration at each point in time, and then in the end calculate how far you've gone. That is expensive, takes a long time. No one has done it for exactly this reason. But the good thing is, once you're up there, you can leave a laser retroreflector up there, as the Apollo mission 15 has done there. That's on the left side there, that nice picture. And then you can shoot a laser at this retroreflector, which reflects light back into the direction from whence it came, and then just measure how long it takes the light to come back. And this is what the picture on the right is about. You have there the Apache Point Observatory Lunar Laser Ranging Operation, which also spells Apollo, which I think is a really great feat of linguistics. And so the precision with this is something like 2 millimeters, I think. So in the range of 2 millimeters. Now, those are three very different ways of measuring. But at the same time, none of these affect the definition of the meter. The definition of the meter might still be, could still be the old one with this metal étalon that you can find in Paris. Of course, nowadays it's not anymore, but in principle, it could still be this. And so this is the core point that I want to just uphold. In a way, this is also not particularly subtle. It's that measurements are inferences about standardized quantities, while standardization itself is concept formation. We develop standards in the way that we develop concepts. Okay, now that's the first part of how things get boring. And the next step then will be to see how this all works out in, well, a very old-fashioned way of doing philosophy of science in the received view of the logical positivists or logical empiricists. So I'm going to look at some general criticisms of the received view, and then at specific ones that connect to questions of how to improve standardizations or how to extend them. And once I've argued that all of this is just fine, we can then look at two short implications of the received view for measurement. One, how we deal with measurement error, and the other one, how we deal with the coordination problem, which we will encounter a bit before that already. Okay, but first, I'm just going to start with, again, something very standard measurement theory. So the idea there is that we have these qualitative concepts like being as long as, here represented by these two columns on the right-hand side. And if two things are as long as each other, then they should be assigned the same value on the length scale. So they should have the same equal length. So LA equals LB, that's the formula underneath. And the same thing with temperature, for instance. So we would say that two objects are in thermal equilibrium. And so again, notationally described with the help of this little equivalence sign here. So A is equivalent to B if and only if they have the same temperature. And so the value on the temperature scale is the same for both objects. Now, the next cool thing that you can do when you standardize a quantity is you can sometimes then you have extensive quantities. And the idea there is that you have this point is that you shouldn't have any air in between, because then the length doesn't actually, then this extensivity of the quantity actually depends on the choice of the combination procedure. So you can't just say length is extensive, but the length equally long should also have the same length values. So equivalence means same value on the scale. If one precedes the other, for instance, one is shorter than the other, then the object that precedes should have the smaller value. And then there's afterwards the summation rule. And once you have that, then all you need to do is choose a distinguished object, for instance, this étalon to the right there, and define this to have the length of 1, for instance, 1 meter, and then you're done. You have a perfectly well-defined length for, well, distances in this case. Good, and note, of course, nowadays we don't use the étalon anymore, and nowadays we use the speed or the distance that light travels in a specific time. So, but that's also a perfectly fine phenomenon that can be assigned the value of 1. Good, and now we can basically look at what this means in a bit more detail regarding standardization. So standardization really just assigns numbers based on basic statements. So we have A equivalent to B and A combined with B and so on. Those are the basic statements. And a standardization then is a definition of a scale in these basic terms. And so the basic terms being the equivalence term, for instance. And a standardization can, in principle, use any unproblematic terms as basic. For instance, extant scale. So if we already have the time scale, then it's fine to define the meter in terms of the time that light takes to travel. Now, the measurement itself, though, usually doesn't actually involve basic terms. So there, instead, we can infer something about basic terms. That is, we can infer statements using the measurements. And these inferences then typically do rely on laws, on theories, and on hypotheses about the measuring device or the measurement procedure. And this is where models come in. And so when the philosophers who work on the new theory of measurement are talking about a model-based approach to measurement, this is very often where it actually comes in, I think. Good. Now, okay, now the question for me is, how can we express all of this in the old-fashioned received view? Well, just a really quick recap on the received view on scientific theories. So the formalization of a scientific theory in this view assumes that we have, on the one hand, theoretical sentences, that is the typical sentences of the theory, which consist of contain logical mathematical symbols and theoretical terms, that is the symbols of the theory on the one hand, and then on the other hand, the correspondence rules, which again contains logical mathematical symbols and the theoretical terms, but then also some non-theoretical or in some way unproblematic terms that are outside of the theory proper. Now, these sentences can be in modal predicate logic and can be in logic of any order. That's sort of just to allow us the full power of mathematics. And the important thing about the non-theoretical terms is that they are directly interpreted. So either formally or informally, the important thing is that they don't depend for the interpretation on the theory itself. So this is basically what is assumed by the logical empiricists, and that was then later sort of rediscovered by the Munich structuralist and by Snead. So the important thing then for them being directly interpreted is that this is in a way the only demand. So they don't have to be observational. They just have to be unproblematic in the context of the analysis. And this also goes back already to Carnap in the late 1930s and to Reichenbach, and then was again rediscovered by David Lewis in his paper on how to define theoretical terms. Good. Now, standardization and measurement in the received view then works also fairly straightforwardly, because standardizations then are these correspondence rules. So the basic terms, thus again, don't have to be observational, which is important because the basic terms in measurements are often not observational. And the cool thing is that this is one of the rare cases of an explicit definability of theoretical terms, because typically we can define our theoretical terms, but when we have a standardization, then we can actually define them. This is really nice. And measurements, again, are inferences. And one thing to keep in mind for what comes next is that therefore new ways of measuring a quantity do not change the meaning of the quantity, because after all, the meaning is fixed by the standardization. Good. And now we can look at some general criticisms. So the most famous one probably is by Fred Sappi in his criticism on correspondence rules, who says that the reliance of the theory on the results and procedure related to branches of procedure. Sorry, I actually can't see this part here. The reliance of the theory on the result and procedures related to branches of science, the design of experiments, the interpretation of theories, calibration procedures, etc., are all being lumped into the correspondence rules. So he says it's all one big thing. And thus, he concludes, there seems to be a reason to suspect that a number of epistemologically important and revealing aspects of scientific theorizing are being obscured. Now, this is odd for at least two reasons. And the first one is that Sappi here assumes that in the received view, correspondence rule somehow must not be further analyzed. And that's odd because it's, well, a bit analogous to demanding, just declaring that in logic, inference must not be further analyzed. So we are not allowed to distinguish further between modus ponens and modus tollens. And that's, I think, what he seems to be assuming here, only for correspondence rules. But the more important thing, point for what follows is that he seems to be confusing the standardization of a quantity and inference about the standardized quantity, because the standardization, that's about the interpretation of theories and calibration procedures. But the inferences, those are about the design of experiments and the reliance on results and procedures of related branches of science. And so, and the former is expressed in correspondence rules, the latter is not. So he's just confused about this, I think. Then we have Patrick Suppes on correspondence rules, who says that, well, who first gives a summary of the received view and then concludes that the most striking thing about this characterization is its highly schematic nature. So first, he says, concerning the theoretical sentences, there are virtually no substantive examples of a theory actually worked out as a logical calculus in the writings of the philosophers of science. And second, which will be important in what follows, the sketch of the coordinating definitions or empirical interpretations of some of the terms is also highly schematic. Now, regarding the first point, he's just incorrect, because he incorrectly assumes that that all axiomatizations have to be exhaustive and have to be done in first order logic. But this is something that he just made up as a demand, and the logical empiricists were actually very happy with accepting his own axiomatizations of theories as well, substantive examples of a theory actually worked out as a logical calculus. So that's just wrong. And the other part is, well, just a bit odd for him to first summarize the logical empiricist view and then afterwards say, well, but that is very much a summary and doesn't go into the details. And yeah, but if he had actually looked at logical empiricists' writings, he could have seen that their discussion of correspondence rules actually anticipate many of the later results, specifically the results that we find now in the new philosophy of measurement. And here's an example about the improvement of standardizations. So this is Aaron Tal, who in a way follows Suppi in criticizing the logical empiricists for not being subtle enough. So he writes that describes, first defines the coordination problem. It says, well, it consists in it that appealing to theory to decide which standard is more accurate would be circular, since the theory cannot be determinately applied to particulars prior to a choice of measurement standard. But since we can only apply the theory once we have a measurement standard, but can discuss the measurement standard only with the help of the theory, and that seems to be a circle. Now he says, continues then that the logical empiricists attempt to escape the circularity by positing a priori statements known as coordinative definitions. This, though, he says, supposes that choices of measurement standard are arbitrary and static, whereas in actual practice, measurement standards tend to be chosen based on empirical considerations. Okay, so now we have the bad guys, the logical empiricists who got it wrong, but now the new philosophy of measurement comes in, and Tal notes that new works set out to show that the circularity is not vicious. Hasok Chang argues that constructing a quantity concept and standardizing its measurement are codependent and iterative tasks. And that seems about right, that these are codependent and iterative tasks. And I always thought that makes a whole lot of sense because I had already read it in Carnap's works. And this is not a particularly subtle or hidden text. It's his introduction to the philosophy of science. And in case you think, okay, well, this is sort of very late in the game. It's also not that, well, first, that's not really relevant. The other thing is it's also not really late in the game because he already wrote about it in the 20s. So Carnap writes the following, that when we examine the definition of M1, so some magnitude M1, we find that magnitude M2 is involved, some other magnitude. So it could be length and temperature, for instance. So, and when we turn to the definition of M2, we find that M1 is involved. So we have exactly the circle or a circle. And, but he has a way of getting around that. He says that the circle is easily avoided by applying what is called the method of successive approximation. The first step is to introduce the concept of length, L1, without considering the correction factor for thermal expansion, that is, without considering the temperature scale. Now, once we've done this, second step, use this concept in the construction of a thermometer to introduce our first concept of temperature, T1. Now, next step, use T1 for establishing a refined concept of L2 by introducing T1 into the rules for defining length, because now we can have a correction factor that takes into account the thermal expansion. Now we have L2 and the next version of length, and that is now available for constructing a more precise scale for our thermometer, and so on. And he notes that it may be necessary to shuttle back and forth several times before the successive refinements lead to measurements precise enough for our purposes. Good. So clearly an iterative and heavily empirical procedure. So no question about that. And we find that again, this iterative procedure and also the highly empirical aspect of this procedure when we look at how to extend standardizations. Here's again Tal. So remember, he says that constructing a quantity concept and standardizing its measurements are codependent and iterative tasks. So we have already looked at that. And then he adds that each epistemic iteration in the history of standardization respects existing traditions while at the same time correcting them. And we have already seen that in a way, because of course, these are the different scales for temperature and length respect the previous tradition to a certain extent. After all, we just add correction factors. But here's another really nice example, I think, from Carnap, who talks about measurements or empirical results regarding a specific predicate. So it says that, oh, and this is testability and meaning, by the way. So he says some laws are discovered empirically within the region of meaning which the predicate in question received before. So we have a well-defined predicate, a standardized predicate, and then we find a specific law. And then Carnap adds, but these laws are extended by convention into a region in which the predicate had no meaning previously. So outside of the standardization, we now extend these laws. And thus, he concludes, in that case, we decided to use the predicate in such a way that these laws, which are tested and confirmed in cases in which the predicate has a meaning, remain valid in other cases. In effect, we use these laws to extend the standardization. And here's an example. Think of, again, the temperature scale. So we start first with a convention, and we say that liquid mercury expands proportionally to the temperature. And then we have this brown line, this brown straight line there in the graph. Now, it's an empirical fact that when mercury is liquid, diluted gases expand roughly proportionally to the temperature. And that's the blue line that overlays the brown line. And now we introduce, so this is where the predicate is well defined, the predicate temperature specifically. And now we introduce a convention and say that when mercury is not liquid, diluted gases also expand proportionally to the temperature. And then suddenly we have a temperature concept that goes all the way where we can for all the regions where we can talk about diluted gases and diluted gases. And the big problem with this is that we have a bit of a Frankenscale here, because it switches from being defined via diluted gases, then to being defined via mercury, then again being defined via diluted gases. So now we can change the scale and by introducing a new convention and say that diluted gases expand proportionally to the temperature. And what was before a fact, namely that when mercury is liquid, diluted gases expand roughly proportionally to the temperature, or a rough fact, becomes now an exact fact by definition. And what was before an exact definition, namely that liquid mercury expands proportionally to the temperature, now becomes a rough fact. So the new scale modifies the old scale, and well, in a way it corrects the old scale, although it's a bit odd to say that it corrects it, because the old scale was not wrong, it was just a different scale. So there was nothing wrong about the old scale, it's just that it doesn't fit, is not exactly the same scale that we used to have. Okay, good. And I think this is, well, this is a fairly subtle analysis of what is going on in measurement. And clearly it is very iterative, and clearly it is very influenced by empirical results. And it clearly is not static or arbitrary. Okay, so overall, I think we can say that the received view just does really well when it comes to measurement. Now we can reap the rewards of that. And here's the first step. We can look at measurement theory and measurement error in the received view of measurement. So here's again Tal on measurement. This is all, by the way, in his Stanford Encyclopedia article. So this is in a way the official statement on measurement in the sciences. So he writes that if quantities had no real values independently of one's choice of measurement procedure, it would be difficult to explain what scientists mean by measurement accuracy and measurement error, and why they try to increase accuracy and diminish error. Well, and this again just confuses the standardization of a quantity and inferences about the standardized quantity. Because of course, if I shoot a laser at the moon, then I might have a lot of measurement error because, well, if I were to lay a bunch of metal bars next to each other, then I might get a different result. And that's just what one would call a measurement error. So standardization is just not the same as inferences about a standardized quantity. But the other thing that I find fascinating is that it, and this is, even within the pure question of standardization, is that it ignores that even basic terms can be vague and they can be known to be vague. So if I have as my concept, for instance, the combination procedure of ringing two metal bars together, two gauge bars together to get my length, then I might just know that this is not completely precise in this, or this is precise is the wrong word here, is that this is a bit vague because it's not completely determined how long my two bars together will be after I've wrought them together. And thus I can know that depending on when the procedure is done, who does the procedure, well, basically I might know that my definition is not completely precise because ringing is not a completely precise concept. So even if I just look at standardization, I can sensibly talk about variations in the standardization. Good. And now I actually want to go back and look a little bit at the inferences about the standardized quantity. And here's one thing that we get out of this whole procedure, and this is we get a really nice, clean way of thinking about measurement. I think that's incredibly helpful. So I think, in a way, this is what philosophy can give us. It can give us more precise ways of thinking about stuff, and it can give us connections that are not completely obvious without it. And so again, start with the assumption that measurement involves an inference. And well, as noted, the premises, the laws involved, the background assumptions may be uncertain, and the inference may be non-deductive. And thus, the conclusion about the sentences in basic terms. If I've measured something and then say, okay, if I were to put this next to that, it would be equally long, something like that. This conclusion is not certain. And what this means is that measurement only provides a probability distribution over the possible states described by the basic terms. So for all the possible ways that now my étalons could combine, for instance, well, I know that some will very probably not be the same length, but for some I'm not completely certain whether they will be the same length. And this is why some of these, why there is a probability distribution over the possible states. And this means that these states described in basic terms can be treated as outcomes in the sense of probability theory. So we have a bunch of possible outcomes regarding the relation between my étalons and the distance of the moon, for instance. And some of them have a specific probability and others have a different probability. And this is just a probability distribution over these different outcomes. And the scales now are defined by these different relations by these different basic statements. And thus we can treat them exactly in the way that we treat random variables in probability theory, which I think is a really clean and nice result. Good, so much for that. And now we can take one more look at the coordination problem, because this is in a way where the tool set and the technical results of logical empiricism then really pay off. And one of the central tools is the Ramsey sentence procedure. And so here we look at any theory, and in principle, as long as it's finitely axiomatized, it's fine. So we can, and here in this case, we look specifically at a theory that consists of basic terms on the one hand, the ones that we use to define scales, and then the scales themselves. So for instance, temperature and length or so. So our theory has then these basic terms and the scale terms, which are just functions. Now, the Ramsey sentence just takes away the scales, takes away the theoretical terms and replaces them by variables. And so you just take all the sentences, leave the basic terms in, take the theoretical terms out and plug variables in. Of course, to make then that into an actual Ramsey sentence rather than a Ramsey formula, we have to do something about with the variables. And what we do is we existentially generalize on these. So instead of saying for instance, temperature relates in such and such a way to length, we can then say there is something and there is something else, such that the first thing relates in such and such a way that is the same way to the other thing. That's basically what the existential generalization does. And the nice thing about the Ramsey sentence, the obvious thing about the Ramsey sentence, is that it uses only basic terms. So no scales are involved anymore. And the slightly less obvious thing, but still a fairly straightforward proof, is that the Ramsey sentence entails the same basic statements as the original theory. So if we are just interested in what our theory tells us about basic statements, then we are all good with the Ramsey sentence. We don't need the theoretical terms. We don't need the scales. And now we can think of the theory as, then now we can think of the conditions of adequacy, C, as part of the theory. So we have the conditions of adequacy for all scales, those we call C, and then the theory is then, we assume, is phrased in terms of the scale, so in terms of temperature and length and what have you. And then that's combined with the conditions of adequacy, and those we just think of as correspondence rules. So our whole theory then, theta, then is the conjunction of the theory itself plus the correspondence rules, in a way as we have done it before, and exactly in the way that it's assumed in logical empiricism. Good. And now we can basically just use the technical concepts. And here's one. So in the theory of measurement, we have these representation theorems. As Roberts in an introductory textbook writes, the first basic problem of measurement theory is the representation problem. Given a particular numerical relational system B, we should find conditions kappa on an observed relational system A sufficient for the existence of an adequate scale. So what this basically means is that we have our theory described in B, that's the numerical relational system, and then we have to find out when we can what relation our basic concepts have to have, so that we can express then the relational system with the help of a scale. Okay, so now assume that T describes the relational system B. So those are our theoretical statements, because they are just involve the scales, the numbers. Now, what Roberts here in effect says is that an adequate scale exists if kappa entails the Ramsey sentence of T and C. Because the Ramsey sentence, keep in mind, doesn't contain any scale statements and just says there has to be something that fulfills these conditions of adequacy C. And this is exactly what Roberts wants from a representation, or calls the representation problem. And so we can, from that, then immediately derive or know from definition theory that T and C, that is a theory plus the correspondence rules, has to be conservative over kappa, over the relations of the observed relational system. And I think that's already a really clean, nice result. Good. And another nice thing that we have is the concept of meaningfulness in measurement theory. So meaningfulness is defined by Suppy's and Zini as follows. They say a statement sigma is meaningful if and only if it retains its truth values under all admissible transformations of all scales. So, okay, so far so good. Now we know that it has to retain its truth values, but we don't yet know what admissible transformations are. And that definition comes from Roberts and Franke. There are actually different definitions, but the best one is from Roberts and Franke, to say that a transformation between scales is admissible if and only if it maps adequate scales to adequate scales. So what this means in our terminology is that a sentence T is meaningful if and only if it has the same truth value for any interpretation of the different scales given the conditions of adequacy C. Okay, and you have to play around a little bit, and then you get that as a result, this means nothing else than that the correspondence rule have to entail that the original theory, that is T and C together, has to have the same truth value as the Ramsey sentence of this original theory. And the reason for this is that, after all, the Ramsey sentence goes through all the different possible scales that fulfill the conditions of adequacy. So has to go over all the adequate scales. And so if it is equivalent to T and C, and then it has to have the same truth value for all these adequate scales. And that is exactly what it means to be meaningful according to Roberts and Franke and Suppies and Zinnis. And thus, Suppesian meaningfulness is translatability under the conditions of adequacy. That's what it means to be meaningful according to Suppies and Zinnis. And thus, here is just a historical point that translatability was the logical empiricist's strictest criterion of meaningfulness. But of course, they had lots of other criteria. And this should, I apologize, my slide is gone. This then should be lead to my conclusion, which you now can see, but then I'll just do it by hand, and I apologize because I can't show you my bibliography. We can, maybe the best is to go back to the beginning and here, give you a quick overview of where we ended up. So the first point is that the received view is perfectly fine as a description of the results from measurement theory. Specifically, it's there is no assumption that measurement standards or conditions of adequacy for scales are in any way static, and they're certainly not arbitrary, that is uninfluenced by empirical results. Another really nice result is that we can think of scales as random variables. Yeah, it's always a bit hard for me to remember random variables because they are neither random nor variables. But so we can think of scales as random variables because they are functions from a probability space, or from an outcome space to specific, for instance, real numbers. And then the core distinction, I think, can really be upheld very straightforwardly, that we distinguish between standardization, which is the development of correspondence rules, and then measurement, which is to make inference about concepts that have been that are connected to our theoretical concepts with the help of these correspondence rules. And once we have set up everything like this, then we can use the logical empiricist's account of how theories are structured with correspondence rules and theoretical concepts, and then use their tools, for instance, the Ramsey sentence procedure, to get a very good grip on both the coordination problem and even the technical problems that Suppies and others have grappled with within measurement theory. And this is it. that's what I think what we get from using the received view to think about measurement, and basically what we get from trying to keep measurement, the philosophy of measurement, as boring as possible.